To complete our discussion of telescopes, let's talk about what I would refer to as non-optical telescopes. This is telescopes at wavelengths other than that you can see with your eyes. And as we kind of mentioned in the preceding section, the atmosphere blocks a lot of the radiation coming from space. We can only see in the optical, this is essentially the wavelengths that can be seen with the eyes, and the radio. So from optical to a little bit of the infrared, especially at high altitudes, to the radio parts of the spectrum are all we can see. All the rest is blocked by the Earth's atmosphere. But we can have other types of telescope. Astronomy can be conducted at any wavelength that's invisible to humans using different types of detector. And we can often get a lot more information from these other wavelengths than we can with our eyes. We can see in the infrared, ultraviolet, radio, gamma ray, or X-ray regions. Infrared astronomy, which is a very extensive field of study, which I've been involved in for decades at this point, uses radiation with wavelengths longer than about 750 billionths of a meter to about 1,000th of a meter. And there's the near infrared and the far infrared. The far infrared is almost a microwave, and the near infrared is essentially heat. So this allows us to see the heat radiation, and this is very useful for looking at spectra, looking at the fingerprints of various molecules and atoms that peak in the infrared. So in terms of infrared images, here's a space shuttle or a human. These are the kind of things that are becoming much more common, that when you are looking at having your temperature taken these days, walking into a building, you will get this from a thermal camera. It will actually image the heat coming from a person and give you an accurate temperature. But infrared detectors are relatively new. They've only become particularly prolific in the last 30 years. And because the atmosphere blocks all but the really near infrared wavelengths, it's best to get above as much of the atmosphere as you can. So here's the infrared telescope facility, a facility I've used myself, which is a near infrared telescope located on Mauna Kea, and as you can see, it's well above the clouds. Well, most of the time. But there's the telescope from within, and you can really see the size of this. And there's the instruments on the back. These are the spectrometers that will take the data from the telescope and turn it into usable spectra, so we can determine the constituents of the stars, nebulae, and galaxies. And there's a nebula, a cloud of gas and dust in the near infrared from the IRTF telescope. And you can see the heat that's actually working inside of these nebulae. You can see stars burning inside this particular material. And that means, as we said, that's in the near infrared. Most of the infrared radiation is still blocked by the atmosphere. And that's where vehicles such as SOFIA, the Stratospheric Observatory for Infrared Astronomy, are used. This is an aircraft with a telescope in the side which is pointed at an object and then by computer control stays tracking that object while this 747 essentially flies above most of the atmosphere. Even then, there is still some blockage from the upper atmosphere. But what can we tell in the infrared? Why do we want to do it? Well, here's Mars in March 1997 in a visual. So this is what you would see with your eyes. If we look at it in the infrared, we actually see quite a different picture. We can actually see this part of the planet is actually much warmer, and that corresponds to the darker part of Mars. So here's a dark part, radiation hits the planet and is absorbed by this dark material and reflected by this lighter material. It's reflected a lot by this polar cap. So we can actually tell how hot parts of a planet are based on these observations. We can look at stars that are embedded inside dust clouds that we can't see with our eyes. So we can see stars shortly after their birth heating up a cloud from within. And instruments such as Spitzer did this. This is essentially a telescope that could be placed in space trailing the Earth or in orbit and look at the heat budget, look at the infrared observations from the stars. And there's some results. Here's essentially an infrared image of a shockwave of a cloud around the star. But of course, instead of infrared, you could use a radio telescope. Now, why would you want to use a radio telescope? Well, there is a big advantage to a radio telescope that light pollution or clouds don't matter to it. Radio waves come through the clouds and any light around us will not affect it. There are some disadvantages. Television, civil and military radio interference, and even cars with internal combustion engines put out radio frequency emissions which can affect your observations. This means that you have to go to rather remote locations away from populated areas to do effective radio observations. And as you can see, radio telescopes are rather large. And here's a sub-millimeter array in Hawaii operating even in terrible conditions. So a radio telescope essentially does the same thing that a visual telescope does. That great big antenna actually reflects incoming radio waves off of its surface onto a receiver, onto a secondary reflector, which then reflects onto a receiver and amplifies the signal, and then we can make observations. And we can look at a whole range of radio frequencies from 3 Hz to 300 billion Hertz, I should say. Unfortunately, the resolution of a radio dish is a function of its diameter, meaning the better resolution comes from very big dishes. So a dish diameter must be very, very large to obtain a useful resolution. So if we want a radio telescope going from 30 centimeters to 3 meters in terms of wavelength, that means we have to have a telescope 100 meters across. So large collecting areas are typical for radio telescopes, which gives us a lot of engineering challenges. If we're looking at radio interference from objects, Jupiter is actually the second biggest radio emitter after the Sun in our solar system. So we actually discovered a lot about radio emissions from the stars, planets and the galaxy during wartime, World War II, when people were looking into experimenting with radar and radio communications much more heavily than ever before, started discovering cosmic signs of interference and trying to screen them out. An example of an enormous radio telescope is the Arecibo radio telescope in Puerto Rico, which is so big that recently a piece of it collapsed. So radio telescopes that are very, very big, such as this one, which is built into a crater, cannot be pointed very easily. The Arecibo telescope has a very limited range of sky that it can look at, and that range of sky is limited by moving the receiving reflector here left, right and backwards and forwards. So there's a big disadvantage that you can't point a massive radio telescope very easily. Consequently, with radio telescopes, people often use a technique known as interferometry, very similar to the technique applied by, say, the Keck telescope, where we combine the signal of two optical telescopes. An interferometry means using two telescopes and combining them to make one large telescope. So two or many more smaller telescopes can actually simulate a much bigger telescope. So something like the Very Large Array, the VLA in New Mexico, which has been seen in I don't know how many sci-fi films, is comprised of multiple small dishes, and they can be moved on a track to simulate a much bigger telescope. You can also use incredibly small telescopes like this and link their signals together and simulate this larger telescope. So a sequence of smaller telescopes like this can simulate a much bigger dish such as this. And that technique is interferometry. Take the signals from multiple telescopes, combine them in a computer, and then simulate a massive telescope. So something like the VLA does this very, very effectively, and you can change the resolution of the telescope by shifting the telescopes on this track. And there's a radio image of an active galactic nucleus from something like these interferometry systems. So this is the center of a galaxy, and we're seeing high energy particles coming out of this galactic nucleus and beaming into space. So in a similar way, X-ray telescopes, when we're going through our spectrum here, and X-ray telescopes have to be space telescopes. These are completely blocked by the atmosphere. So they are very high energy telescopes, and they're also very, very useful. They tell us about the highest energy reactions, or close to the highest energy reactions in the universe. Here's Jupiter in X-ray showing its aurora as the magnetic field of Jupiter picks up charged particles and dumps it on its poles. Areas around black holes are very active in the X-ray as material falls into the black hole and heats up. And the last telescopes we'll discuss are the highest energy ones, which are gamma ray telescopes. And these don't use optics at all. These look at very, very high energy photons. And again, this is a relatively new field in the last 30 or so years. And they use what are referred to as Cherenkov detectors. And this actually looks at photons passing through materials of different density, looking at the energy as light passes through these various different density materials. So something like the glass telescope. And what do they detect? Such things as gamma ray bursts. These are the most luminous events in the universe since the Big Bang, since the inception of the universe. And these are flashes of gamma rays, incredibly high energy sources from very, very deep space. And these are seen to occur at very random times and locations. These are very mysterious to astronomers even now. And there are many, many theoretical ideas as to what causes these. Collapses of a star, possibly black hole formation. And there's the kind of image that you can see, the afterglow of a gamma ray burst. So, when looking through this set of slides, you should really think about at what wavelength would you actually look at the stars? What wavelength would you be particularly interested in? And where would you actually put your telescope to observe at that particular wavelength?